I'm Sean. My job is to kind of start where Morby left off, talking about how to explain the formation of the solar system and look outward at extrasolar planetary systems and see what we got, what's out there, how it might have formed, what's going on, and kind of what stories we can tell about. If we understand planet formation, then we should hopefully understand why the solar system looks one way and most extrasolar systems look other ways. So that's where we're going. And right, there's a movie here. So there are not very many movies in exoplanets that are actual real movies. This is one of the few that is actual observational movie. So you can see, I don't know if you can see too well, there's the date going by on the bottom left. These are real observations of the HR 8799 system. And so you can definitely, I don't know how well you guys can see it, there's 4 planets here. So they're named B, C, D, E from the outside in this case, because they were detected from the outside in. Usually they're inside out, but in this case they're outside in. But that's B out there, C, D, and E. And so this is a system with 4 kind of really big gas giant planets. They're each 5 to 10 Jupiter masses or so. And I'll talk more about it in a minute, but it's kind of neat. There's not very many movies that are like real data in exoplanets. And this is, in my mind, the nicest one there is. So I'll just let you enjoy it for a minute. Enjoy. All right, let's move on. So this is what I have planned to talk about. And in reality, I plan to actually talk to you about number 5. And then if time allows and people are interested, I can talk about these things. Okay, so here's the plan. At the beginning, I'll give you kind of half, basically my public talk version of how we find exoplanets and what they look like. Then some information about observations of planet-forming disks. Then I'll get to kind of the more technical models of how planets form, the different categories of planets that we see. We'll talk specifically about super-Earth systems, then about systems with gas giants, and then I'll talk about kind of water delivery, how water gets onto planets that are predominantly rocky in the habitable zone that might have aliens on that we're all really interested in, really. And so kind of mechanisms by which this happens in the solar system, and then extrapolating which mechanisms are relevant for other systems. And then if time permits, like I said, on my blog, I did this kind of thought experiment about how many habitable planets you could have in a given system that I may or may not lead you through. I've also spent the last few months thinking about this new interstellar object, and I could tell you about that if we get there. Okay, so moving along, how do we find planets? There's more than this, but these are kind of the techniques that I'm going to talk about. The 2 main ones, really, that dominate the field almost entirely are radial velocity and transit. And then there's also microlensing and direct imaging. And this is just a nice picture of Kepler's Space Telescope. All right, so the radial velocity method, right? All of these methods, or at least the first 2, radial velocity and transit, are indirect methods. So we're not taking a picture of a planet around another star. You're measuring something about the star as it moves or does something in reaction to the presence of a planet. So the most obvious thing that you see in this movie is that while the planet orbits the star also orbits the planet, just on a much smaller orbit. And so that's what the radial velocity method tries to find, is that motion of the star around the planet, or really around the center of mass of the star-planet system. And then you can see at the very end, the line of sight is moved so that you can see the planet passing in front of the star. And that's going to be the basis for the transit method. Seeing the light from the star have little blips because planets pass in front of it. So this is kind of the basis of the radial velocity technique. So you got a planet going around a star, but all we measure is the star. And we don't measure everything the star is doing. All the radial velocity method is measured basically the Doppler effect, so the line of sight velocity of the star, either towards you or away from you. So when the planet is here or behind the star is still moving, but it's moving sideways, so there's no shift. When the planet's moving this way, the star is moving away, and there's what's called a redshift. When the planet's here, the planet's moving away, the star is moving towards us, there's a blue shift. And how is this measured? In practice, it's measured by measuring a whole zillion spectral lines of the star. And the tricky thing, the technical part of it, is how to reference those. So you can see the real star's lines moving compared to something that's not moving. And there are different techniques about that. And there's some new ones involving laser combs that are supposed to do this much better. But none of those actually work yet, but they're in the works. So currently, the best instrument that does this can measure precision of a given, with a given measurement of about, say, 20 centimeters per second on the star's velocity. So the smallest amplitude signal that has ever found a planet is a couple meters per second, which is the speed of kind of a medium-paced walk, which is not too bad. And just for scale, the amplitude, the radial velocity amplitude of different types of planets I kind of listed here. So for the Earth, it's about 9 centimeters per second induced in the sun. For Jupiter, it's about 10 meters per second. For a hot Jupiter, it's something like 50 meters per second. And since this is from the public talk part, you get to see some pictures of telescopes. This is the ESO 3.6 meter telescope in Chile that has the HARPS instrument, which is one of the best radial velocity instruments out there right now. And here is the data for the first detected exoplanet around a main sequence star, 51 Pegasi. And so the curve that you see, basically this is the velocity of the star as a function of time. And you can see the amplitude here is something like 50 meters per second. And so what kind of information do you get out of this? Well, ideally you watch until this thing repeats. So you get a periodicity out of it. So that's one thing, right? That's how long it takes the planet to go around. And then the amplitude tells you something about the mass. Okay, so that's the information you get from this technique, gives you the period and the mass. You don't get the exact mass, you get a projected mass, because it's typically referred to as m sin I, because it depends on the orientation of your line of sight compared to the planet's orbit. If a planet's orbit is basically face on, then the star's wobble is very small. And so then you would underestimate the true mass of the planet. Whereas if the planet's orbit is edge on, you're seeing the full effect, and so you get basically the true mass. You can also get information on a planet's orbital eccentricity, its orbital shape, from the radial velocity curve. And so here on the left, we're looking at different configurations of different orbits, with different eccentricities here. So a circular orbit and two orbits with eccentricities of 50%, but with different orientations. And so you can see this is the radial velocity curve on the right. So the simple case, like I showed you before for 51 Peg, is basically a sine curve. It's nice and regular. And you can figure out that's more or less a circular orbit. For eccentric orbits, they can take different shapes depending on their alignment. And so kind of these weird different shapes correspond, these two correspond to the same orbital eccentricity, but different alignment in terms of where the planet's basically accelerating relative to your line of sight. But that's another key, basically, piece of information that you try to get out of radial velocity measurements is the eccentricity, the shape of the orbit. The second technique that's super important these days is the transit method. And so this is, if you happen to be watching a star and you're looking in the plane, the same plane as the plane of a planet's orbit, the planet may pass in between you and the star, and the brightness of the star goes down. Right? It's a pretty simple idea. Then, the amount, basically the magnitude of the dip tells you something about how big the planet is compared to the star, right? Assuming you know the size of the star. It's really basically the ratio of the radii squared. And then the periodicity, if it repeats, tells you something about the planet's orbital period. And so, the information you get here is fundamentally different than a radial velocity technique. You don't get almost any direct information about planets' masses. You get something about their sizes, which is complementary, right, in some cases. And so, for example, the best precision right now for really bright, stable stars with the best instruments can measure changes in brightness of stars, on the order of a few 100,000ths. That's a hard word to say, 100,000ths. Anyhow, so you can do that. You can measure that kind of level of precision, which is what you need to measure things that are Earth size around sun-like stars. So the Earth is about 1 part in 10,000 blip in the brightness of the sun. Jupiter is about 1%, and a hot Jupiter is also 1% because it depends on the size of the planet, not where it is. Right, a hot Jupiter would repeat much faster than a Jupiter, but the amplitude of the dip would be the same. And what's interesting is Earth is about 10 to the minus 4 for a sun-like star, but for a very puny star, it's about 1%. So that can be useful. We'll see that going forward. So the most successful transit mission to date was NASA's Kepler mission. This is just nice pictures of it. This is its launch. You don't really care about that. wait, I have this thing here. So here's one thing that's interesting about Kepler is its field of view. So in the sky, its field of view is here. All right, this is the Milky Way galaxy. The disk of the Milky Way is viewed in the sky. That's Kepler's field of view. And here's kind of a cartoon view of it. And it's kind of interesting to think about why it chose its field of view. So Kepler, what is it? It's a camera that was trying to capture as many stars as possible within its field of view and measure their brightness every half hour for as many years as possible. Okay, so basically it wants to pack as many stars as possible into a given field of view, but not so many that stars are on top of each other, because then there's a blip in brightness and you don't know which star it came from. So there's a kind of a compromise between lots of stars, to pack get as much information as possible for your square degrees on the sky, versus confusion. It's called confusion, when you have too many stars, you can't tell which one's which. And so if you're just going for numbers of stars, you go along the plane of the Milky Way, because that's where all the stars are in the galaxy. But you don't want too many. So they aimed about 5 degrees off of the plane of the Milky Way to balance these things. Interesting tidbit. And here's kind of one iconic system that was discovered by Kepler, the Kepler 11 system, which has 6 planets that are all smaller than Neptune, basically. They're typically, I think, 2 to 4 Earth radii or so in terms of their sizes. And they're on a relatively compact configuration. The 5 innermost ones all fit inside the size of Mercury's orbit around the sun. And the 6th one is just a bit further out. And this is kind of an iconic super-Earth system that was discovered by Kepler. And we'll talk more about this type of system. So the gravitational microlensing technique, we're not going to talk much about it, just here to illustrate the idea. On the top here, you're seeing a light curve of a background star. So here's the setup. Our telescope is on the bottom, and some very distant background stars out there. And a star with a planet orbiting it, because of the proper motion, passes along our line of sight. So what happens is, because of general relativistic things, basically a star can act like a lens and focus the light, which acts to increase the brightness of the distant star, because you generally can't resolve the different images that are created. Yeah. So in reality, there's lots of little images that are created, but typically you can't actually resolve them, and so the effect is just to brighten the background star. So what happens is the background star gets brighter and brighter and fainter. In the middle, there's a little blip. And that little blip is the same process. This kind of longer effect of brightening is caused by the star. The blip is caused by the planet. Kind of the width, the time, the duration of this kind of event is directly tied to the mass of the object, effectively. So very short duration blips can be planets in some cases, whereas the longer ones are typically stars. And the duration here is typically like a month or so for a star, something like a day or 2 for a planet. Okay. And here's one example system that was found with microlensing. This is a very complex event where they were able to determine that there were 2 planets orbiting a given star. The star was somewhat smaller than the sun, but if you scale it by about by about their temperature, how much light they get from their star, it was roughly in a Jupiter-Saturn analog. It's kind of a neat one. Oh, I forgot to put the reference of it. But, and I've actually forgotten the reference also. So anyhow, you can Google it if you want. But microlensing technique is very promising, and it can find planets in a whole kind of different region of parameter space than those other techniques. But to date, it's only found maybe 10 or 20 planets, something like that. Finally, direct imaging. So the challenge here is, if that's your star and that's your planet, you can't see it too well, right? Because the reason is just that the planet's orbit is kind of within the star's light. It gets drowned out by the light from the star. It's within the, no matter how well you can't get rid of the light of the star to see the planet. And so in practice, what's going on here, there's basically diffraction spots from the objects that overlap so you can't see them. Right. In some cases, though, there's clever techniques to block out the light of the star to try to see the planets. And that's what we saw, like, for example, in this movie. So this is that HR 8799 system, in which there are 4 planets that have been found. All these weird kind of speckly things in the middle, those are just small artifacts from the suppression of the star very close in. And the things that are moving systematically, those are really the planets. So this system has, it's a very massive star. It's an A star. And it's relatively young, something like a couple hundred, or maybe 100 million years old, something like that. And each of those planets is thought to be 5 to 10 Jupiter masses. So they're really big guys. Anyhow. So now I'm just going to lead you through just a few interesting exoplanets that have been found before we get into more detail of the demographics of what they look like. So here's a plot of just kind of the sizes of planets. So some very small planets have been found. These are just planets from two systems, the solar system and Kepler 37 system. So in the Kepler 37 system, the smallest planet that's been found is smaller than the size of Mercury. And so it's kind of neat that Kepler is sensitive to planets that are that small. And it's only the case for the stars that are really bright and really quiet for Kepler, so that they're able to basically get a good enough signal. But you do find planets kind of all sizes going down to very small sizes. This is one of my favorite systems, Kepler 444. I just think it's kind of weird. So here's an illustration of 6 different planetary systems, roughly to scale. Here's a logarithmic orbital distance axis here. And so the solar system is at the top, small rocky planets close in, bigger ones further out. Then there's lots of these super Earth systems that we'll talk about later that typically have planets that are a little bit bigger than Earth on orbits that are pretty compact. And here's Kepler 444 down there. They're all puny. They're all smaller than Venus, I believe. And they're all packed within 1/10 of an AU. And the star is also like 11 billion years old. It's really weird. It's got a lot of weirdness, this one. So I don't have any big answer as to what it means. It's just an interesting weirdo. Yeah.
Can you assume that there are other planets, but you haven't detected them over the time of observation of the Kepler?
So we'll get to that in a sec. But the idea is, yeah, with the transit method, you only find planets that you're very biased towards finding close-in planets. So there could easily be planets further out here that we don't see, or here. We're pretty sure there aren't any here, though. Although Planet 9 would be out there. Yeah. So there's lots of observational biases. It's tricky. There's only some cases where you can be quite confident that there's no other planets, at least in a given range within a given system. So for example, imagine like these 2 planets here, the outermost, the orange guys. Their orbits are clearly pretty compact. So based on dynamical arguments, you could say, is there any possibility there could be another planet in between them that we would have missed? And given that they look really close to each other, I would guess not. And then you could say it's unlikely that you missed anything in between there. But there's a gap. It's not impossible there could be another planet in there. You can study the effect that planet would have on the orbits of the other planets, see if that's consistent with what you observe. So there's kind of indirect ways to address that. But just from a purely detection probability point of view, it's not that easy. Great. Oh yeah, I put this in here. All right, I'm just going to start this. This is a movie they made of Kepler. I never get anything out of watching this. Do you guys? You guys probably are, though. Huh? There's even music. So it's just the point of this diagram is to show the kind of diversity of Kepler systems. Right, the solar system is up here on the right just to kind of give you a scale for the sizes of orbits, the relative sizes of planets. They're obviously not to scale on the same scale as their orbits. And the color corresponds to how hot planets are. And so the solar system has no planets that are hot on this scale. Why is that? It's because these methods are so biased towards finding close-in planets that all these planets that we find are really hot compared to the ones we have. It's partly observational bias, but it's partly that there's planets there. To me, it's just like too much going on. But you guys seem to enjoy it, so I'll leave it for a minute. All right, we'll stop there. Oh, next, so I got this slide from Franck, who didn't show up today. Anyhow, so obviously, has anyone not seen Star Wars? Because if so, you have to leave immediately. No, I'm just kidding, it's okay. All right, so obviously this is an iconic image from Star Wars, the 2 suns in the sky. And a cool discovery from Kepler was planetary systems like that. Right. Obviously, the only part we know about is the 2 suns in the sky part. So this is the Kepler 47 system for scale. The green ring is supposed to represent the habitable zone. And in the Kepler 47 system, there are 2 planets. They're both giant planets, so not small rocky ones like in Star Wars, but still, They're giant planets that orbit, instead of orbiting one star, they orbit around 2 tightly bound stars. So these things really exist and we really see them. I think there's 10 or 20 of them known now, something like that. There's also a lot of orbits that are very different than our own. Here's a very extreme case. This is the HD 80606b planet. And so this is the shape of its orbit compared with the orbits in the inner solar system. So you can see, it looks really different, right? It's really, really stretched out. And so why is it so stretched out? Well, the leading explanation for why most planets' orbits are stretched out is that they probably form on relatively circular orbits because they form in these big disks of gas that are very dissipative. And so things tend to go towards circular orbits. But then a system that forms more than one planet can go unstable, kind of like a Nice model instability, but even on a bigger scale. And when that happens, a movie starts. Right? So when that happens, the shapes of orbits kind of jiggle around, and you can have 2 orbits cross, which means 2 planets can be in the same place at the same time, which does not necessarily mean, especially in this regime, does not mean a collision. It means a series of close gravitational encounters between gas giants. And the last one gave a big gravitational kick. One of those planets flew off, never to return, to interstellar space. And the one that survives has a stretched out, eccentric orbit. And so I like to say these eccentric orbits are basically scars of these planets' violent pasts. But you have to say it kind of in a low voice when you say that. Sorry. All right. And so an interesting thing is you'd expect from this kind of idea that there would be a counterpart, right? For every time you have an eccentric orbit that survives, there was one that got kicked out. Do you see those ones that got kicked out? We do, actually. So we don't see a ton of them. They're hard to find. There's about 20 of them that are known now. They tend to be found in young star clusters, where you kind of look for isolated things that are not associated with a star. And then you can find ones that, since they're so young, they still have a little bit of heat left. And there's, I think, about 20, the last time I checked, of these that are known. There was one claim from microlensing that these were super duper abundant, but that claim was recently refuted. So at one point, in 2011, there was a paper saying that these were more abundant than stars in the galaxy. And now we know, and that confused everyone because it didn't match up with that idea, given that there's not enough gas giants on eccentric orbits to explain them. But now that measurement has been disproven, and so they still exist, but at a much lower rate than we thought a little while ago. So now just a couple words about observational biases. So these plots are showing kind of the biases inherent in the 2 key techniques, the radial velocity and transit techniques. So for radial velocity, the kind of relevant x and y axes that are typically shown here are some mass versus orbital separation, sometimes semi-major axis, sometimes orbital period. And so what these plots are showing, they're kind of showing an artificial survey that's idealized of how well you could do detecting planets. So each of these kind of little faint blobs is a star with a planet. And the ones that are thicker or solid, they're the ones that were detected in a given 1-year observing survey. That's idealized. So this is done in a computer, not a telescope. It's just to illustrate the biases. And so basically, this is the parameter space that is available to radial velocity surveys. The longer your survey goes, the more widely, you can find planets on wider and wider orbital periods. But it's hard to get to wide periods and low masses, for example. You're generally biased towards short periods and high masses. That's the bias inherent in that technique. The transit method has a slightly different curve here. So now instead of mass, we have radius. So the size versus the separation in period again. Whoa, it's like shaking. And so again, each of these kind of faint gray dots is a planet around a star, and the solid ones are the ones that are detected. So you can see you're much less likely to find a planet within this box than you are here. Radial velocity will find pretty much not 100%, but a large fraction of the planets within its given search box. Transit detection will not, because for every, I guess Earth is a good example. So for every Earth around another star, even if your telescope is sensitive to blips that are that depth, there's only a 1 in 200 chance that it actually transits. So the odds that that the alignment of that system works is only about 1 in 200. So it's much harder in some sense to find planets by transit because of that. And there's actually, even though there's strong biases towards finding close-in planets with the radial velocity method, they're much stronger still with the transit method. And you can see that because there's very few of these blips that are found out there. There's also a hard cutoff at the survey duration because it depends on your criterion for exactly what you call a planet. Right? If you find a blip in the star, the planet goes around, you see another blip. Usually 3 or 4 blips are enough to say there's probably a planet there, depending on how well you characterize the blip. Right? But if you only have 1 blip that does not repeat, you can't find the planet. So if you have a survey that lasts 1 year, you have 0 chance of finding a 2-year period. Whereas in the radial velocity method, you can actually get a hint of that, get a hint of where a planet is without seeing the full phase coverage. All right. So this is just to illustrate that these methods are very powerful, but they have inherent biases. And these are taken into account when we figure out occurrence rates of planets. These biases are taken into account. Yeah?
I'm confused, but what are the fake dots? This is
this is
not real data.
No. So this is a fake simulation that Josh Wynn did to illustrate this. So it's just like in this idealized case, which ones do you find? And yeah. So there's planets everywhere, but you only find them in different places. Yeah. So this is it's kind of disturbing to think, what's going on here, that you can't find as much as you want. So for example, an interesting, the Kepler mission was designed, it had one goal, which is to measure the occurrence rate of Earth-sized planets around Sun-like stars. And so Kepler has found a zillion things and really revolutionized exoplanetary science, but it failed in that goal. It was not able to measure that. At least people are still trying to go back through data and figure it out. But there was a little bit more noise than they had anticipated, and they'd gotten an extension to double the length of the mission to really do this well. And then one of the gyros died and they had to switch. So the Kepler mission, for example, did not do that. And one reason why is even if this curve is extended much further out by having a 4-year, 8-year mission, you can see most of the planets, for every planet out here, you're not finding most of them just because the transit probability is really low. Everyone seems really disappointed now. Sorry. All right. So anyhow, here's what we got. As of, I guess it's a few years old, but it hasn't changed too much. So in terms of planet mass here versus orbital separation, with some kind of transformation to put transiting planets and RV planets on the same graph, here's what we got as of more or less right now. So I believe the red ones were found by transit, and the blue ones by radial velocity, and the green ones by microlensing, and that one's probably by direct imaging. So what do we got? I put our own solar system planets on here to give you a little bit of a scale. So Earth and Venus are here, Jupiter's there, Saturn's up there. And so, well, we don't have anything that's quite Earth-like yet. Right? There are things that are getting closer and closer. This edge is basically moving outward in time. But it's hard to do because you need very good surveys, very good data over a long period of time. The only solar system planet that you can kind of hope to find is Jupiter. And there's a handful of good Jupiter analog systems. And just to kind of lump these into groups, this is generally what I'll refer to for these different clumps of data. All right, so these clumps, like these clump of bodies up here, these are objects that are very massive, very close to their stars. They're typically called hot Jupiters because they're very massive and on very hot orbits. All right, these are kind of normal Jupiters in terms of being Jupiter size or Jupiter mass, but further away. And these guys down here are very, very abundant. And I typically call them hot super Earths. That's not the greatest name because they're not necessarily Earth-like at all. There's some of them, the smaller ones that are less than maybe 1.5 Earth radii, less than maybe 5 Earth masses or so. A large fraction of those seem to be rocky. The bigger ones seem not to be most of the time. Most of the ones that are bigger seem more like scaled down versions of Neptune. And they're sometimes referred to as sub-Neptunes or mini-Neptunes, that kind of thing. So here I'm kind of lumping them all in as hot super Earths, but there's really a diversity within that. And here is my little cartoon of the demographics. Oh, but you can't see it very well. Oh. So this is kind of one way that I like to break down the what we know, and that is just starting from sun-like stars, just breaking down the different systems we know and the occurrence rate into classes. So here, the thickness of a given line corresponds to the occurrence rate, roughly. Okay. So starting from here, we're at 100% of sun-like stars. Then we can ask the question: what fraction of those have gas giant planets? So planets that are at least, say, as massive as Saturn or so. And that rate is something like 10%. Right? I put little squiggles next to everything because, give or take a factor of 2, something like that. But it's not 1% and it's not 80%. It's around 10%. Okay? Then from those, you can ask what fraction of those have Jupiter-like orbits. That is, orbits that are relatively circular and relatively wide. And depending on the cutoff, you get something like 10% of those. So that's about 1% of all of them. So I don't know if you guys can see. If you squint, you can see there is a line there. And so that line thickness is 1% as thick as that one. All right? Because about 1% of stars like the Sun are seen to have Jupiters that are broadly like ours. Something like 10% of stars like the Sun have Jupiters on orbits that are very different. They're often very eccentric, like I said. Sometimes they're hot Jupiters. The hot Jupiters are not terribly abundant, but there's some. And then the other ones that don't have gas giants, at least that we haven't found yet, a lot of those, something like half-ish of all of sun-like stars, have these super-Earths or sub-Neptunes, things that look broadly like this shrunk-down picture of the Kepler 11 system. Okay? So this is kind of a very simplistic way to break down what we know about exoplanets. But it's nice in terms of putting the solar system in context. So we know the solar system is not like a 1 in a bazillion case. It seems at the moment to be more like a 1 in a 100 kind of case. Yeah. And this is only just from Jupiter's orbit that we're doing this, not from everything. All right, let me move on. All right, so as you'll see, I should have said this at the beginning. So this whole introductory part about exoplanets is just kind of randomly jumping around to different pieces. So it's a little bit discombobulated. So sorry about that. So now we're jumping to the habitable zone, which is kind of a different thing. Just to give you I'm just giving you little small snippets of things that are interesting in exoplanet observations right now. And then we'll get to the models in a minute. So habitable zone is kind of, the region of orbits around a star where it's good, if you have the right kind of atmosphere, there's a possibility of having liquid water on the surface. And what's interesting about that, among other things, is that it scales with the brightness of the star. So this is kind of to scale around different types of stars, how big the habitable zone is. And so, for an M star, a very small star, it's much smaller than for a star like the Sun, which is a G-type star. And why do we care about this? Because those observational techniques, remember, are very biased towards finding planets close to their stars. And that counts, if your star is small, that still works. And so it's much easier to look at the habitable zone of this guy than of this one. Right? And so the first Earth-sized planet around in the habitable zone of another star, I don't know if this was the first, but it was one of them anyway. It was this Kepler 186 system. In this case, the star was an early M star, for those of you who know. Kind of a star that's about half the mass of the Sun or so. And I was going to show you this movie just for what shows up later. But no, I'll skip it. So there's many of these that are known now. There's a few dozen habitable zone planets that have been found that are, within, say, 50% of the size of the Earth. And here's some of them as of 6 months ago or so. And you can see on the y-axis here is the type of star. So the Sun is right around here. Oh yeah, I guess the Earth's there, so you can tell. And on the x-axis is basically the orbital distance, in some sense, as measured by the energy received by the star. Okay? And so those green bands are, different estimates of the habitable zone. And so there's a few of these that have been found. And each of them is very interesting in its own right. And I'll just kind of highlight a couple of them because they're interesting. Sorry? So a couple of just interesting cases that have been found in the last couple of years are, I see I'm going kind of slow. All right, I'm going to go relatively fast through these ones. So the closest star to the Sun, Proxima Centauri, Proxima Centauri, it's only just more than 4 light years away, was just recently found to have a planet about the mass of the Earth. You can all see Proxima Cent on this image right there. It's the closest star to the sun. It was only discovered 100 years ago. This is Alpha Centauri A and B. They're kind of on top of each other in the southern sky. I don't know which one that is. Someone probably knows here. Not important. Anyhow, Alpha Centauri is a triple system. It's interesting. There's 2, close to sun-like stars on a relatively tight orbit, an orbit the size of the orbit of Neptune around the sun, and a much more distant star, Proxima, which has an orbit that's about 10,000 AU in size. And that's the star around which we recently found this planet. And so here's the data. All right, this is the data from the Discovery paper. This is the radial velocity signal. You can see the amplitude here is small. It's about 5 meters per second, half semi-amplitude there. And the whole big thing that was all over the news was from this little peak. All right, that's basically the Fourier transform of that data. Right? And so that's the evidence we have for, did I put the details of it? No, I didn't. Anyhow, so it's a planet on about an 11-day period, something like that, but in the habitable zone of its star. And so its star is just very small, and so that's within the habitable zone for that star. I was going to show you this whole TRAPPIST-1 movie, but it's kind of long. You guys already know all about TRAPPIST-1? Should I skip this thing? You want to see the movie? Okay, all right, then you can see the movie. So TRAPPIST-1 system was discovered last year, or at least the outermost planets were discovered last year. It's a very puny star. It's barely a star. And I believe this shows you the actual data. We got 3 consecutive weeks with the Spitzer Space Telescope to observe this thing. And so this is the actual data. And so it's very tricky. You can see the blips you see are often 2 planets at once. And so an interesting story is that they initially thought that the 3rd planet out was actually a double planet, like 2 planets orbiting each other, because they kept seeing blips where there were 2 planets happening at once. 2 signals at once, basically. And they thought it could be a double planet. But with a much longer baseline of observation, they could figure out which blip went with which planet and figure out what was going on. And so the movie keeps going. Oh, there's even several triple blips. Oh, I don't know if that is one. But there's some where you have a triple trans at the same time, which are pretty cool. All right, I'm getting bored. We're going on. Sorry, I have the little clicker. Anyhow, this planet, this system is super interesting for a couple reasons. From a kind of astrobiology point of view, what this plot shows is the relative scale of the solar system versus TRAPPIST-1 in terms of the amount of energy received from their star. And so the Earth is here, and there's different estimates of the habitable zone. At least kind of these 2 planets are really firmly within the habitable zone. Maybe even 3 or 4 of them are in the habitable zone. So there's many planets in the habitable zone. What I think is more interesting is the orbital configuration of the planets. So all 7 of these planets are in resonance with each other. And so you heard Morby talk about resonance a bit this morning. That's kind of a natural outcome of planets when they form within gas disks and migrate around. They often end up in resonance. So here there's a system with 7 planets all in resonance with each other. So it's what we call a long resonant chain. And we'll talk more in a minute about where those come from. And so that's the longest resonant chain that we are aware of in the whole universe. Except for in my simulations. No, I'm just joking. That was unnecessary. All right. So, now see, I totally put these things in the wrong order. I should skip this part. All right, I'm going to skip this part because I should have put this earlier. This is internal dialogue. Here. This is just kind of a cartoon version of where planets form. Okay? So looking up at the sky, what constellations are we looking at here? Usually I can figure it out. I can't figure it out this time. Anyhow, so this is a nice set of images made by Kees Doulemond, just kind of zooming in to show you the scale of star formation and where planets really form. Okay, so this is a very zoomed out picture of the sky where you can see the Milky Way, you can see these different features. If you know about which comets were in the sky at different times, you can tell this is from the late 90s when Comet Hale-Bopp was around. Okay? And then we're going to zoom in on different parts of it into the Eagle Nebula. This is one of these classic images taken by, I think, Hubble. Or is it just the zooms that are taken by Hubble? We're going to keep zooming in here. So we'll zoom in on that part. This is the famous Pillars of Creation image by Hubble. And we'll keep zooming in here. This is, a big cloud of dust that's actively forming stars right now and interacting with nearby bright stars that are basically evaporating gas off of this side of the cloud. And we'll keep zooming in to that little bitty finger of gas. And that thing there, like 1 pixel, is the size of our solar system. So this is just kind of put in context, the larger context of zooming in on where the action is, where stars and planets are actually forming. And obviously within there, we imagine this kind of stuff of disks with stuff swirling all over the place and bashing into each other and forming planets. So I've been around, so that's the end of the first part. I've been very slow getting through that. So I'm going to go a little faster through this part. So what do we know about protoplanetary disks, where planets actually form? So here are some early images from the 90s of disks seen edge on around young stars. And so here, these are really pretty images. And that kind of black part that you see, this looks like kind of a sandwich or something. So the thing in the middle of the sandwich is dust. So we're looking at a disk edge on, and the dust is blocking most of the light from getting out. But the disk kind of is flared and has some puffy parts further out. And so you can see light scattered off of those puffy parts. And sometimes you can see cool jets coming out of these disks. They're really cool. Recently, the ALMA radio telescope is really revolutionizing the field of observing disks around young stars. It's taken several kind of key images. So these are both images of few million-year-old disks around stars that we think are basically forming planets right now. And kind of the initial thing that you notice is that these don't look like smooth things. There's a lot of structure in there. There's pileups where dust is drifting around. And so here what's interesting to note is these kind of empty holes are, they're relatively empty, and they're empty in the dust, which is what's being probed here. We're not seeing large objects, we're seeing dust. And this is another one, TW Hydra, and it's even able to zoom into the very innermost parts. And it looks like there's a little mini cavity in the very innermost parts of the disk that's kind of on the scale of Earth's orbit around the sun. And in some cases, some disks are seen to have kind of spiral structure, and they look cool. All right. Statistically speaking, we have some information about the kind of the properties of disks that form planets. One thing we know about them is that disks around massive stars tend, on average, to be more massive. So this is the mass of the disk as a function of the mass of the star. And you can see there's a rough trend. Now, the rough trend is really much more visible because of the gray band and the line. If you didn't have that, you'd see like, oh, maybe. Right? It's not as obvious as that because there's a lot of scatter. So it's kind of, there's a trend, but there's a lot of scatter at a given, oh, oops, I threw a button. There's a lot of scatter at a given mass. Yeah. What else is there? Wait a minute. That's the same. This is just a little bit more data, the same thing. Another thing that we know that's super important is how fast disks go away. So disks don't last hundreds of million years. The gas is gone, we think, within 5, 10 million years, something like that. And how do we know that? We infer that indirectly, actually, from the presence of hot dust. So what this plot shows is for each of these points is a cluster, a young cluster of stars. And what's shown on the y-axis is the fraction of stars in that cluster that have disks. And so very young cluster, basically in very young clusters, all the stars have disks. And once you look at 10 million-year-old clusters, almost none of them do. Right? And so basically the time scale for the disks to go away is something like a few million years. There's also outer disks of debris and stuff. But I feel like I'm getting off track here. So I'm going to skip over that. And we'll jump to the more planet formation-y stuff. All right. So that was all warm-up just for planet formation stuff. I think I was a bit slow going through that, but here we are. So stages of planet formation. Here's a very simple cartoon of the different kind of steps in planet formation. And we're not going to go through all of them. It's just to kind of give you a picture of how we get from A to B. That it's not a simple thing, and there's lots of things going on. So starting within a disk of gas and dust around a young star, dust coalesces to form kind of millimeter, centimeter sized things called pebbles. And they don't really look like pebbles on the beach. It's just kind of get you to remember the name. Those pebbles, obviously, they drift, they interact strongly with the gas and drift inward relatively fast. They can also be, they're concentrated into forming things like planetesimals by the streaming instability like Morby talked about this morning. Then they can grow into larger bodies, things like planetary embryos. These are the Mars-sized objects that Morby was talking about. And sometimes much larger. They can be up to Earth mass or more in some cases. Then, remember, this is happening within a disk of gas and dust. While the gas is still around, these objects can migrate. Right? They can launch density waves in the disk and migrate around. They can also become gaseous planets, gas giants. Gas giants can also carve gaps in the disk and also migrate. Right? So here, this planet carved a gap in the disk and then gets pushed around by the disk during its evolution. Once the gas goes away, systems with many planets can go unstable. So this is a kind of cartoon version of that animation of many planets in the same system that go unstable. One of the planets gets kicked out, and the one that survives has an eccentric orbit. Then you can also have kind of later giant impacts between large bodies that are still around. And you kind of have the final formation of terrestrial planets. At least in the solar system, we know this happened long after the gas went away. So I'm not going to talk about every little detail here. Morby already covered a good chunk of this stuff. So I'll talk about how we can use different parts of this, kind of different puzzle pieces in some sense, to address specific questions, to talk about where super-Earth systems came from and what might be going on in systems of giant exoplanets, stuff like that. All right, so super-Earths. So here's another plot of the super-Earths that we're aware of. As you can see, there's a lot of these things. So in terms of size, not mass here, and orbital semi-major axis, this is the distribution we got. And, oh yeah. So these are things that are generally called super-Earths. So you can tell they're typically between 1 and 4 times Earth's size in terms of radius. And the clump is really big. I guess it's easier to see without that. It's big, and it's not that well defined on its outer low mass parts, but there's a lot of planets in there. Something like half of all sun-like stars, actually half of all main sequence stars are found to have super-Earths. And you can see the Earth itself is out here. Venus is would be what, 987 here. And so we don't, they're still beyond the edge of the distribution. But there's a lot of things in there. So what else do we know about them? Well, this is the distribution as a function of different size. And it's kind of interesting to see in terms of planet size, it looks like there's a dip. So there's a lot more of them when you go to smaller sizes, but then it's not just a flat distribution, there's a little blip. And the interpretation of that blip is unclear. These ones that are right around the size of the Earth are thought to be mostly rocky. These ones out here are thought to have more mini Neptunes, something like that. So these would be more super-Earths, these would be more mini Neptunes. And exactly what you infer from the blip in there is up for grabs right now, I would say. Here's an illustration of a few different super-Earth systems. Okay, so these are just ones that I grabbed from the Kepler catalog just to illustrate the orbital configuration of these systems. Okay? And so it's a log scale on the x-axis. What that means is that distance between two planets can be read off as the period ratio. So the ratio of the period of the two planets. Okay? And so you can see, they're generally on relatively compact orbits, but they vary a bit. And on the bottom here, I have this solar system that I've just chopped all the orbits by a factor of 10. Right? So this is not exactly where the planets are, but the separation between planets is the same. So you can see the Earth to Venus orbital period ratio is kind of similar to the period ratios that we see among these other planets. Okay? So the question here is, how did they get there? All right? So I'm going to go through different ideas for how these super-Earth planets may have formed. Yeah? And we'll evaluate the different ideas. So here's one kind of simple cartoon way to do this. In terms of kind of parameter space without putting any axes on here. Just in terms of the size and orbital distance, how did things get there where we see them now? 1 to 4 times the size of the Earth on pretty close in orbits. Well, maybe they just grew where they are. That's called in situ growth. Maybe there was just a lot of material close to stars, and things grow right there. That's kind of the simplest possible model you can think of. And it's the only punchline of this whole section is that that model can't be right. But I'll explain why. All right? Maybe material kind of comes from far out, like Morby was talking about with pebbles drifting inward through the disk. And maybe they stay small and they only actually grow close in. So in this case, you'd still have most of the growth of planets pretty close in, but the mass would be coming from further out. All right, I'll call that kind of the drift model. All right, that's the idea there. Or maybe it's kind of the opposite, where things are able to get relatively big, relatively far out, and then they migrate in which case most of the growth would happen relatively far out, but things would then afterwards migrate inward. So those are kind of the three classes of models you can think of, or that I'll talk about. Yeah. So remember, the punchline here is, let's first test this in situ accretion model. Okay. So let's see what would happen if things do form in situ. So if they form in situ, that means that there's a decent amount of mass very close to the star that's able to grow into planets. Okay? It's a pretty simple thing. We can test that in a computer. Here's a computer simulation, orbital eccentricity versus separation of a bunch of rocky things that just start off close to a star, and we're going to see them bash into each other. Okay? So here we go. They bash into each other, and they grow, kind of as a wave sweeping outward, more or less. And you can see the time up here. This is happening really fast. These inner planets were more massive than Earth within like 1,000 years, like ridiculously fast, like super duper fast. And then at the end, we form things that are, a few Earth masses. That inner one is 6 Earth masses. That one out there is 0.3. Okay, so the key point there is how fast things happen. So they happen fast. So they happened so fast that the gas disk was still around. Remember, those gas disks last a few million years. Those planets were growing in a few thousand years. That means they were growing and still big while there was still a lot of gas around. Okay? So the gas matters. So as a function of size, growing from dust up to big planets, the gas matters. And so here's kind of a very cartoony way to illustrate how much the gas matters at different sizes. For things that are tiny little dust grains, they basically go wherever the gas goes. So they don't really drift compared to the gas. But those pebbles drift super fast compared to the gas. And larger objects don't drift too much. And then big planets, say Neptune-sized planets, they drift really fast. They migrate instead of drifting. So this is gravitational instead of aerodynamic, but it's the same kind of thing. So fast drift, kind of slow. All right, why does this matter? Well, it matters because in this in situ model, you can basically calculate if a given planet formed there, and it formed fast, how fast should it be migrating? And how fast it should be migrating is shown here. Okay, so this is just a time scale. Each of these is kind of a given super Earth planet that we know of. And so all these are the time scales of how fast they should migrate in their disk, assuming they form where they are. And these times, basically the important thing is that the times are very small. The length of the gas disk is up here, is several million years, and these things are way below it. So what does that mean? Boom. It means that if super-Earths, if they really form where they are, then they must have interacted really strongly with the disk, right? And if they interact strongly with the disk, they have to migrate. And if they migrated, they didn't form where they are. You see where I'm going here? So it's kind of it's not a self-consistent picture. It just doesn't make sense to think of it that way. If they form in situ, then they can't be where they started off. It's really it's not logically consistent. So the punchline here is things did not form in situ. They could have done a large part of their growth there from bodies that drifted inward, but they can't have really grown locally from really massive progenitor disks. Okay. So the second idea is this drift model. Okay? Here's a cartoon of that drift model. And I'm not going to talk much more about the drift model, but I do like the idea. It's not as well developed as the migration model, so I'll show you more results from the migration model. Also because it's us who are doing the migration model, so I have better graphics for it. So. Anyhow, the idea is this. Here's kind of snapshots in time. Basically, pebbles drift inward in the disk, and the key idea is just that they don't just disappear. maybe in some cases there's a way that the pebbles may be trapped. A large fraction of the mass in pebbles that drifts may be trapped. Instead of just kind of going in and heating up and vaporizing, they may be trapped. So what would trap pebbles? Something like a pressure bump. What is a pressure bump? Basically one of those regions where aerodynamic drag is reversed. So instead of a headwind, you go from a headwind to a tailwind. And right at the transition from headwind to tailwind, stuff gets trapped. So if there's one of these, and there's a good reason to think it's not a crazy idea that there could be a trap like that close in. If that's the case, then many of these pebbles could be trapped there. And you could pile up just kind of a whole bunch of small pebbles until you have enough material to form planetesimals and then planets there. And so that's the idea. You form generations of planets by that sort of process. So the planets, like I said, would actually grow close in, but the material would have been sourced from further out. So it's not the same as in situ growth. It's stuff that drifts in and then grows close in. So I think it's a plausible model. It remains to really be demonstrated whether it really works. But the idea is pretty nice. Yeah. The model I'll tell you guys more about is the migration model. And so you already heard about the general idea of migration. Here's just kind of a snapshot of a simulation with 5 different Earth mass planets within a disk, and they're each launching their density waves and migrating around. Yeah. And so remember, migration happens for, say, Earth mass or larger planets or so. And it's driven by these density waves that kick the planets around. And a key thing is, even if migration is inward, migration is often directed inward, but it doesn't mean that planets migrate onto their stars. Yeah. So why is that, right? You can imagine if the disk goes all the way down and touches the star, then it should be possible for planets to actually migrate onto the star, maybe. The thing is that we don't think that disks do that. There's a lot of lines of evidence pointing to the fact that disks have inner edges. And we think those inner edges are typically about 10 or more stellar radii from the star. So there's a big dynamic range between the star and the inner edge of the disk. And so this is one particular model by Flock that's really nice. But there are others. And the details of exactly what's going on here are not very important. The key idea is just that migration does not go all the way in the star. Instead, migration goes and stops there. Okay? There's no way to push the planet on the star. Even if you happen to kick a planet hard enough to make it go past the inner edge of the disk, which actually happens sometimes in our simulations, then there's no more gas in there. So there's nothing to push it on the star anyway. There's things like tidal evolution with the star that can change its orbit, but it's not going to make it fall on the star like that. So here's kind of a cartoon version of the migration model that Morby and I and others have worked on. All right, we call this one breaking the chains, just to give it a dramatic name. But also it means something, because the chains are resonant chains that you know about now. So here's the cartoon picture. Mass versus orbital distance. Starting from small bodies, they grow. They grow larger planetary embryos. These are things like Morby talked about, probably Mars mass things closer in, larger things that are similar to the cores of the giant planets further out past the snow line. Those guys are big enough to migrate, and that's what they do. They migrate inward and form chains of orbital resonances. And usually the innermost planet is pretty close to the inner edge of the disk. Okay? And the innermost planet kind of holds back the other ones. And they don't bash into each other, they get trapped in resonances. But then this is all within the gas disk. The gas disk goes away after a few million years, and those things, they have a kind of a late instability. There's often collisions between them, and they end up on a wider non-resonant configuration. And this is what we see. So here's an actual simulation. In this case, what we're looking at is a bunch, just the outer ones, right? This simulation doesn't include the inner ones, just the outer ones from past the snow line that are going to migrate inward in time. This is, again, mass versus separation. And these curves here are zero torque curves. So within these curves, migration is actually outward. It doesn't end up mattering too much here, but in principle, there's a little bit of outward migration that's possible. So here we go. So things kind of migrate inward, and you'll see there's occasional collisions between these guys. And once in a while, they feel the outward migration zones, but sometimes they don't matter too much. And they go until they get anchored at the inner edge of the disk, just like I was talking about. And they end up in these long chains of resonances. So in this case, at the end of the disk phase, this one just goes for while the gas disk is still there. And I counted them the other day. I think there's 11 planets within half an AU. And they're all in resonance. And if you go further out, there's, I don't know, 12 or 15, I don't know. So this is a very long resonant chain of planets. And like we saw earlier, some resonant chains must survive. Things like TRAPPIST-1, right? These are in order. Here's all the resonances in the TRAPPIST-1 system. 7 planets all in one long resonant chain. So some fraction of those survive. Okay. So the whole breaking the chains idea is that all systems pretty much of super Earths form these resonant chains, but then a lot of them break. And what breaking means is they go unstable, and then there's a late phase of collisions after the disk is gone, after the gas is gone. And so at the end, it's not in resonance. Oops. And we can test this model with observations of super Earths. So this is showing the period ratio distribution. So every time there's 2 planets in Kepler around the same star, you look at what the period ratio is between those and add them up. Yeah? And this is what you get. It's this distribution. And you can tell there's not that many things in resonance. How can you tell that? If there were, there would be kind of big steps at 3 to 2, or 2 to 1, or 4 to 3, or 3 to 1, something like that. And there's not. You can tell there's actually little blips. There is a little blip at 3 to 2 and 2 to 1, but that's about it. Okay, there's not that much else. Now here's our simulations, those simulations I was talking about. The red ones are basically those resonant chains, okay, while the gas is still there. Okay, and so you can see those steps. Those steps mean that there's a lot of planets are in a given spot. They're very common to be in 3 to 2 resonance or whatever they are. Okay? And then sometimes they go unstable, and when they go unstable, they end up on much wider orbits, which is this blue curve. Okay? They're much wider. All right? And so the idea is that using these kind of simulations, mixing some fraction of unstable systems with stable ones, we try to match the actual observations. And when we do that, play that kind of statistical game, what we find out is, I like the things that come from the top. Anyhow, what you find out are you need about, a factor of 10 to 20 to 1 mixing of the blue to red ones. So about 90 to 95% unstable resonant chains, 5 to 10% stable ones. And if that's the case, we can match all these things. Yeah. So that's the migration model. And it's nice, it works pretty well. Yeah. There's obviously issues, and it's constantly being revised when there's more data and more ideas, but for the moment, it seems to work pretty well. Right? There's obviously more to the story with super Earths. This is a cool paper showing that what this result is showing is basically that a lot of super Earths are mini Neptunes. So this is kind of the super Earth to mini Neptune transition in some sense. So what we're looking at here is a statistical study. So none of these points on its own is that convincing. It's more the ensemble of them that's telling a story. So for each of these planets, these are different individual super Earth planets. The y-axis is the fraction of its mass in a gaseous envelope of hydrogen and helium. And the x-axis is the size. And using statistical models to try to match the mass and radius at the same time. What you can see is the small guys are consistent with being purely rocky. The big ones are consistent with having a lot of gas, being really mini Neptunes. And there's a transition in between. And this transition is at something like 1.5 to 2 times Earth's size. And the typical kind of fraction of the total mass in gas is like 1%, something like that. And this can be explained, I think it can be explained pretty well by atmospheric loss during giant impacts. And what this plot is showing is kind of the fraction of an atmosphere that's lost as a function of impact energy, basically. And impacts typically, it's common to lose something like half of an atmosphere in a large impact. And why is this interesting? Basically, you can match the distribution roughly with just a small number of large impacts. All right. Carry on. So that's the general idea, is impacts seem to be able to explain this kind of general thing. Although there's still a debate about exactly what, the source of all the differences between super Earths and mini Neptunes and what it means. finally, I was going to tell, in the same kind of story, I was going to tell you a similar, well, the same kind of result that Morby mentioned this morning, but in cartoon version. So the same picture that I showed you earlier of the migration model for super-Earth formation can be applied to try to put our solar system in context. And how is that? So starting from this kind of distribution of planetary embryos, what happens if the innermost big one grabs onto a bunch of gas and becomes Jupiter? Well, in that case, it carves a gap and it basically blocks the migration of the outer ones. And so these guys are trying to migrate in there and become super-Earths, but they can't. Instead, they're blocked by Jupiter or by Jupiter and Saturn. Instead, boom, everything looks great. Right? And so this is what Morby was talking about. From this point of view, the ice giants and maybe even Saturn's core in the solar system can be thought of as kind of failed super-Earths because they were trying to become super-Earths and Jupiter blocked them. And it's nice. A nice thing about this idea is it makes a prediction. All right? There's a clear prediction that there should be an anti-correlation between systems with lots of super-Earths and systems with distant Jupiter-like planets. And this is kind of on the edge of being statistically testable with the current data set. All right, this slide is just to kind of illustrate, how much like Earth are these super-Earths anyway. So just kind of listing a few key properties of these things. The size range, formation time scales are definitely different for super-Earths. They probably typically form, within the gas disk lifetime or a little bit longer. Say, by 5 or 10 million years, super-Earths are done forming, whereas Earth took more like 50 or 100 million years to finish forming. They often have significant atmospheres, whereas Earth doesn't. Composition's uncertain, tides. This is kind of, if you want to think of, how much like Earth are super-Earths really. These are kind of some of the factors that come into play. It's not all of them, but some of them that matter. I feel like we should stop to have like a margarita break or something. All right, I guess I'll just have some water. Okay, all right, here we go. So now we're going to kind of look at systems with giant exoplanets. Okay. What do we know about those, and what can we learn and kind of extrapolate about what they mean? So here's what we know. What this is showing is actually, I don't think it's the number. I think this is actually the corrected. I think it's the occurrence rate as a function of distance. And so basically, something like 10% of Sun-like stars are found to have gas giants. And most of them are past around 1 AU. So this is the distribution as a function of orbital separation. So there's a little blip here of hot Jupiters. About 1% of stars have hot Jupiters. And then there's not that many here, out to about half an AU. And then going further out, there's a ramp up. There's a lot more around half or 1 AU. And that plateaus. And out here, there's that strong observational bias against finding these planets because they're in such wide orbits that they're hard to find. So this decrease out here is at least in part due to observational bias, but this increase here is real. So there's really kind of a lot of planets out there. And there's there's more small ones than big ones, so there's a lot more Saturns than Jupiters or super Jupiters. It's also interesting to note that lower mass stars have fewer gas giant planets. I couldn't find a better plot of this, but this tells you kind of the key thing. As a function of the mass of the star, so kind of Sun-like stars, low mass stars, high mass stars, there's a very strong trend in terms of the occurrence rate of gas giants. They seem to be much more common around more massive stars. Even low mass stars have very few Jupiters, but they do have just as many Neptunes and super-Earths. Okay, so that's kind of interesting. And here's their overall eccentricity distribution. So eccentricity versus orbital separation of the known giant planets that are at least 1/10 of a Jupiter mass, so 30 Earth masses or larger. And Jupiter is on here for scale. And so, you can read the mass sort of in terms of the color. But the key thing that you notice is Jupiter's down here, and there's a lot of planets up there. And there's a lot of planets in there. And we think that this diagram can be explained mainly by two key processes. One of them being orbital migration, like we talked about, and so orbital migration would basically cause Jupiter-like planets that formed here to go inward, and dynamical instabilities, also called planet-planet scattering, that would cause planets to go up by giving them higher eccentricities. And actually, I'll just mention this. In terms of where hot Jupiters come from, there's a little bit of a debate. There's a model, the simplest model is that, or no, I shouldn't say simplest. One model is that they form out here and then migrate inward. And another model is that they get scattered to very high eccentricity, such high eccentricity that they actually get close to the star, on their closest approach to the star. And in that case, they can interact highly with the star and end up as hot Jupiters. And there's kind of these two ideas. And there's an observational way to kind of get at this. There's no final answer, but there's an observational way to start looking at this. And that's from this effect called the Rossiter-Mclaughlin effect. Okay, so this effect, I was telling more of you, I did this experiment. I talked about the Rossiter-Mclaughlin effect in a public talk a few years ago. And at the end, I asked people what fraction of the people understood what I was talking about. And it was 0. So if one of you gets this, then I'm way above what I did last time. All right, so the Rossiter-Mclaughlin effect. So we've talked about the transit method and the radial velocity method. And the Rossiter-Mclaughlin technique combines the two. So it's neat, it's both of them at once. So what the Rossiter-Mclaughlin effect is you start from a system where a planet transits in front of the star. You know that the planet transits. And what you do is you measure the radial velocity during the transit. Right? That's the signal, radial velocity during a transit. So why do you care about this? That's what these plots are showing. Okay, so here's the star. All right, and let's assume that this, the star's spin axis is more or less straight up. Right? And the star is spinning. Right? Remember, the radial velocity basically measures the Doppler shift. So if the star is spinning, there's a part of the star that's coming towards you that's blue shifted. That's why it's bluer on this plot. And there's a part that's red shifted. Okay? So the star is spinning, blue shifted, red shifted. So what we usually measure is an average. And it's smeared out, and it doesn't care about the spin of the star. Right? Or not for what we care about anyway. Okay? But now let's imagine a planet's transiting in front of it. All right, so this planet's pretty big. When the planet, let's say the planet's on an orbit like this. When the planet starts to cover a little bit of the star, it doesn't cover the star uniformly. It covers just one little piece of it. So at the beginning, if the planet's going this way, it'll cover a blue part of the star. What does that mean? That means if you measure the overall Doppler shift of the whole star, you're taking away a little bit of the blue part. So you end up giving it a red shift. All right? And then as a function of time, that changes. Right in the middle, it goes to 0. And on the right side, you're blocking a little bit of the red shifted part of the star. So your signal is blue shifted. And so what does that look like? In terms of the radial velocity as a function of time, this would be kind of the average curve. But with the transit, you block a little bit, goes up. Then right at the middle, it's canceled out. Then it goes down.
But just in case, the planet have relatively big size to the star, right?
Yeah, exactly. So the planet's size is key. If the planet is tiny, then this effect is tiny. And it's hard to measure. Yeah. So it's easier. Everything, or almost everything in exoplanets starts off with hot Jupiters because they're big and they're close in. And so these measurements were first done for many hot Jupiters before attempting it for any other kind of planet. But now it's doable for Neptunes and a couple super Earths too. But yeah, that's a good point. So you can see that kind of general argument, all right? But now, what about this case here? If the orbital shape is a little bit different, if it's crossing the star like that, then the shape of this, the Rossiter-Mclaughlin signature is different. And then you can have really weird ones. Very highly inclined orbit that here it only crosses over the red shifted part. And so it makes a blue shifted signature, but no red shifted signature. And so the punchline here is that the Rossiter-Mclaughlin effect gives you some information about the inclination of the planet's orbit compared to the star's spin axis, or really its equatorial plane. So you can imagine there's some configurations where there would be no signal at all. So imagine you measure this and it's actually completely flat. So there's at least two ways to do that. Imagine the planet's orbit is exactly vertical and it goes right down the pipe, right down the middle. Then you would always be blocking an equal amount of blue and red shifted and you can get to 0. Another possibility, so that would mean that the planet's orbit was basically polar. Its inclination would be basically 90 degrees compared to the equator of the star. Another case where you get the same thing is imagine you're just actually looking at the star pole on. Then there's actually no red and blue side. And so then any orbit will always, block, the same signal. But both of those cases end up with polar orbits. And so if you see, orbits where basically your inclination is 90 degrees. And you can also have the same thing where imagine the exact same orbit, but it's in the opposite direction. Then you'd have the same signal, but opposite, so we go down first, then up. And that would be a pure retrograde orbit. And so these things are measurable, and they have been measured now for, 100 objects or more. I don't know the latest. All right, so now let me see. How many of you guys got what I said? Yes. All right, this is a great success. This is good. At least it's more than 0. That's good. All right, so here's some information. This is actually a bit old. I couldn't find a new one. But anyhow, this is from a handful of hot Jupiters. So we're looking at here is basically that angle, the angle between the planet's orbit and the star's equator, projected. All right. So that angle, so 0 means everything's coplanar, 180 means it's perfectly retrograde, 90 means it's basically kind of polar. And these are a bunch of hot Jupiters. Right? And so this is a cool paper from 2010 where it was suggesting that most of these guys had a very low inclinations, and most of these ones had high inclinations. All right. So what does this mean? This is basically these are all hot Jupiters. These guys seem to have orbits that are well aligned with the equator of the star, and these ones don't. And there seems to be a transition at a certain temperature. So the x-axis here is stellar temperature. So the sun is about here, 5,800. And so these are, what is it, F stars or something like that. These are like K stars, something like that. So there's this transition. And the hypothesis in this paper was that it was related to tidal dissipation. So they thought this was good evidence for that idea that tidal dissipation, going from a very eccentric orbit, tidal dissipation with the star to shrink the orbit was the source of the hot Jupiters. Why do they think that? They were saying that the convective zone of the star, which is maybe where most of the tidal dissipation within the star happens, shrinks as a function of the different stellar type. And so for stars that are hotter than this, they have very little convective zone, so presumably much less dissipation. So, basically as the orbit gets shrunk, there's less recentering it in some sense and putting it in the same plane. That was the idea, the hypothesis that was put forth in this paper, and it seemed to work pretty well. Since then, there's still a lot of debate, and I don't think this issue is closed at all. But it was kind of an interesting way to use this new type of measurement to test this idea. All right, so that's the idea. All right, I already showed you this plot. So back to this kind of thing, in our distribution of eccentricities, there's these two key processes that are thought to shape the distribution of where giant exoplanets are. And so one question to ask is, if these processes are really important, then what effect do they have on the rest of their planetary systems and the formation of, smaller planets like Earth? And so let me show you that. So here's just a simple plot of an animation. We're going to show this. The y-axis is the eccentricity versus orbital separation here on a log scale. And the color here corresponds to water content, very roughly calibrated to match the present day solar system, where everything closer than a couple AU is dry, and further out things have a little bit of water. And Jupiter's out here, but this guy's going to migrate. Okay? And so you can see it migrates inward. And so as it migrates inward, these vertical lines are different resonances with the giant planet. And so those act basically as kind of snow shovels to push stuff interior to them. So they push material closer in. But sometimes things get a little unlucky. They get a little too close to the to the Jupiter and get kicked outward. And then the thing that's also doing the pushing is there's gas drag accounted for here. Sorry, also. And that kind of basically helps the whole snow shovel effect. And so at the end of this movie, this Jupiter has migrated through all this stuff and pushed about half of it inward and kicked about half of it behind it. And the stuff that it kicked behind it is very, well, you can't see it too well here, but it's very kind of rainbowy. There's lots of different colors on top of each other. All right, and that matters. I'll explain how in a sec. So now let's look at the same kind of thing, but on a much longer time frame. That was for the duration of the migration phase of maybe 100,000 years. And so looking on a longer time scale, you can see what happens to the whole planetary system. So here, I'll do the same kind of run as before. The only difference is there's a little bit of outer stuff, and the simulation goes for much longer. So you can see, boom, the migration's super fast, boom. And then the disk sticks around, in this case, for 10 million years before the gas goes away. And you can see the gas helped damp the eccentricities of those scattered bodies. And they form they're starting to form a second generation of planets. And then the disk goes away and everything goes kind of bonkers. But, planets are still forming here. And so in this, even closer in than this close in Jupiter, there's a, really close in rocky planet that formed from a mixture of all this stuff that it plowed through. And then it scattered all this stuff beyond it. And that stuff that scattered beyond it kind of formed a later generation of planets. And this guy is interesting because it's, it's on more or less an Earth-like orbit. It's at about 0.9 AU, a little bit more massive, but it's got a lot of water. It's got about something like 20 times more water than other simulations that match the Earth. And so why is that? Why did that happen? It happened because as the Jupiter migrated through it, it stirred up everything out here and basically caused this very broad mixing of stuff from different zones. And so, here's a cartoon version of what it might look like with a hot Jupiter in the sky and all that. It's pretty. All right. So another, you guys already saw this movie. So this planet-planet scattering is really important. This effect, it's not just pretty movies. We think that this applies to at least 3/4 of all systems of giant planets. And we need to invoke this mechanism to explain the distribution of their orbital eccentricity. We think it's super common, and that's the source of the vast majority, at least, of eccentric orbits that we see. Now, you might ask, why should systems go unstable? That seems really weird. And here's a little cartoon that I made of this, of why they might go unstable, just with simple arguments. And so here's the idea. Basically, we know pretty well from simulations and stuff like that giant planets tend to form with kind of characteristic spacing, and they tend to form close to the edge of stability. They tend to kind of end up getting packed as they migrate, as close as they can be without going unstable. Okay? But the thing is, as everything evolves, one thing that's keeping them stable is the gas. I like to think of the gas as like a teacher, and the planets are like little kids at recess. So the teacher's like watching over them, like, don't mess around, don't mess around. But then in time, at some point, the teacher goes away. And so when are things going to go crazy? When the teacher goes away. So what the punchline here is basically this transition. When the gas goes away, when the teacher goes away, that's the trigger for things to go nuts. All right. So that's the natural trigger for instabilities is when the gas disk dissipates. Okay? And that's part of what is so weird about like models for the solar system with a late instability is really weird because it's hard to explain a late instability. It's much simpler to understand why instabilities happen early. Oh, and someone once dared me to put oh yeah, all right. How many of you don't recognize this picture? Oh no. Yeah, okay, good. All right, it's from the Karate Kid. Anyhow, I was once dared to put a slide of the Karate Kid in a talk, so that's where that came from. Anyhow, so that's the idea. So things go unstable. It makes sense that they usually go unstable early, but not always early, but it makes sense. Okay, so let me show you an interesting example. This is actually a kind of an unusual example because the instability won't happen that early, but it'll happen. So we're looking at here is a similar simulation of stuff that's trying to form terrestrial planets in here. So rocky material, like basically following the old Wetherill model of terrestrial planet formation. Instead of just Jupiter and Saturn, it's Jupiter and 2 Saturns and an outer disk of planetesimals. And don't worry too much about this panel. It doesn't really matter for what we care about. It's just the dust flux coming from collisional evolution of this stuff. So here we go. So everything stays well behaved, and these objects, these planetary embryos are bashing into each other to form larger and larger planets. And the outer parts of the disk are getting sculpted by gravitational interactions with the outermost giant planet and everything. And you can see things kind of bouncing around, and then the movie slows down, and then boom. So that's an instability, of course. And so I chose this example because so most of the rocky material was dumped onto the star. But in this case, I chose this one because you're an astrobiology audience. Because in this case, one planet did survive. It's kind of hard to see, but we'll zoom in on it in a sec. So one planet survived on a very weird orbit. It's a very, very eccentric and inclined orbit. So its eccentricity is always bumping up and down. And its inclination actually goes from about 0 to 60 degrees every 10,000 years, something like that. So very big oscillations in terms of its orbit. But its orbit is perfectly stable. And its size, I think it's more or less Earth size and same orbital radius as Earth, even though it's a very different orbit than Earth. And this is interesting in terms of astrobiological things because of the climate possibilities on this kind of thing. So an interesting thing to think about is on Earth, climate variations over 100,000 year timescales are largely controlled by changes in just relatively small changes in Earth's orbit, both the obliquity, the eccentricity in particular. And they're called Milankovitch cycles. And so it's interesting to kind of imagine on a planet that had relatively large orbital oscillations what the climate would do. And so this is a little experiment we did a few years ago with Dave Spiegel. Dave Spiegel led this. And a key thing here is we tested what the effect would be of a very extreme case, just to kind of illustrate what could happen. In this case, a planet's orbit oscillated between an eccentricity of 0, perfect circle, and an eccentricity of 0.8 or 0.83. So it's a very extreme case, but it's just to kind of illustrate it. And what's interesting to note is the orbit average flux. The amount of flux that an orbit intercepts depends on its eccentricity. It doesn't usually matter much until the eccentricity is very high. But when it's pretty high, it does matter. And so here's a little climate model that Dave ran that I think is kind of funny. And so in the climate model, here's the planet. And the colors correspond to different, basically different temperatures. So green is everything that's, you would think of as habitable, where you can have liquid water. And blue is super cold, and red is just pretty cold. All right. And so remember, when we go to 0 eccentricity, that's when the flux is actually lowest. And so here we go down to a nice circular orbit. And this thing falls into a snowball state, where it's just an ice ball. And that makes its reflectivity higher. It's what's called albedo gets much higher. And then it's kind of stuck. It's stable, being super reflective like that. But then as the eccentricity gets higher, it tries harder and harder to thaw out. And eventually, it's going to happen. Oh yeah, so there you go. So there it finally made it out of this snowball state. And in this big band around the equator was able to have this kind of area where it was nice for liquid water anyway, before plunging down into, freezing cold again. So this is kind of an interesting connection between, orbital dynamics and what might be going on with the climate. And obviously this is a very extreme example. It's just to illustrate one process of many that's at play. I think I'll skip this one. So now I'm on to phase 5 of what I was going to talk about. Okay. So this is the last phase that I'll try to actually get through. So we're going to shift gears a little bit and talk about water delivery to Earth and other Earth-like planets. Okay? And so I'll kind of talk about different processes and then focus on whether they make sense in the context of Earth and where else they might make sense. Okay? So first off, how much water does Earth have anyway? All right, that's a good thing to know if we're going to try to match it. Well, on the surface, Earth has what's called one ocean of water. That's a unit of water that's basically all the oceans on the surface put together. And so we know we have that on the surface, but how about in the interior? In the mantle, there's a debate. Some people think there's very, very little water. Some people are really convinced of this. I guess all the references got shrunk way down, but Wendy Pinero in particular tells me there's impossible for there to be more than a couple tenths of an ocean in the mantle, whereas some people think that it's likely there are 5 or 10. In the core, likewise, there are very strong opinions about whether there's almost no water or a lot. And maybe some of you know more than me about what the right answer is. But as far as I can tell, it's really up for grabs exactly what Earth's bulk water content is. In any case, taking numbers that most people are relatively happy with, the total water mass fraction of Earth is something like 1/1000th of the Earth's mass. Right? Something like that. And the distribution of water in relatively primitive bodies in the solar system looks like this. So this is water content in log scale versus orbital distance. And so we think stuff that started off on close to Earth's orbit was very dry. Things that are, the inner part of the asteroid belt is quite dry, and the further out you go, the more water things have. Okay? And so C-type asteroids tend to have, 10% water by mass, something like that. Whereas, actually, I believe ordinary chondrites have something like, 1%? You probably know. Or less. A little less than that, okay. Anyhow, and then further out, comets, main belt comets and normal comets can have much more water. And there's chemical constraints in terms of isotopic ratios of the water, in particular nitrogen isotopes, hydrogen isotopes, typically the D to H ratio. Okay. So our general setup looks like this. You're going to imagine, so we're going to come back to a plot like this a lot. It's really simple. This is the Earth right now. Its current equilibrium temperature is 255 K. But we think that water within the disk had to come from further out where it was colder. Colder than something like 150, 140 Kelvin. And so this is kind of an illustration of the problem. To be in the habitable zone, you got to be nice and warm. But to get water, you got to be really cold. But to be habitable, you have to have water. So that's kind of a trick. Like, how did water get to the habitable zone where we want it on Earth and other habitable planets? That's what we're going to talk about. So I'm going to talk about 4 mechanisms. I'll call them pebble snow, wide feeding zone, external pollution, and inward migration. And others exist, but I won't talk about those. Okay? These are the ones I'm going to focus on. Okay? So first one, pebble snow. Okay? And this can be illustrated with this sort of picture, which is the snow line. Right? So on this mountain, it snowed. Right? And this line here is where the temperature was about 0 degrees when it was snowing. Right? Then when it stops snowing, the temperature can be anything it wants. It's not snowing anymore. It doesn't matter. It could be 0 degrees down here, but if it's not snowing, you're not going to get snow. Okay. This is Morby's idea, so we'll see how he likes my explanation of it. Anyhow, so the idea is this. All right, like I was saying, within a planet-forming disk, there's a kind of critical distance, often called the snow line, beyond which water can be a solid. All right? And closer in, it can't. Closer in, it can only be vapor, basically. It's too hot. Okay? And so the temperature structure within the disk is important. The temperature structure is determined by things like viscous heating from friction within the gas, irradiation from the star. That kind of stuff determines the temperature structure within the disk. And here's what models for the snow line's location look like. This is one example, but there's a whole class of these things that all look roughly the same. So we're looking at the snow line distance as a function of time. And so depending exactly what your sources of heat are, in any case, the snow line moves inward. And late in the disk's lifetime, after a few million years, models have the snow line in at around 1 AU or even closer in. Okay. So basically, disk evolves, it cools down, this kind of snow line moves inward. And so in terms of our habitable zone planet and our separation as a function of time, looks something like this. Right? Early on, the disk is relatively hot, the snow line's far away, and then in time, it sort of moves inward. And things that are there can get a bit more and more and more water. Okay, so that's the idea, that as the snow line evolves, you can get water. So where does this water come from? So it's a little tricky. So like I was saying, any water that's close in, can still exist, but it'll be vapor. It won't be solid. So interior of the snow line, water can only be vapor. The trick is, all this gas is moving around within the disk as the disk evolves. And it turns out that this wet gas is moving in and typically falling on the star much faster than the snow line is moving. Right? So what does that mean? It means that the source of water here is not this gas. Right? It has to be coming from somewhere else. And as we heard about, a more likely source than this gas is some small bodies, pebbles, drifting inward from further out. So that's the idea. We think that the source of water here, it's not stuff that's just jumping from there, gas jumping out, getting colder and condensing. It's small things getting delivered from further out. The thing is, there's other stuff going on out here. So imagine, the snow line moved in a little bit, but you're growing bodies, you're growing planets, right? You're growing things like Jupiter. And once Jupiter gets big enough, it blocks the flow of these pebbles, like Maury talked about. It makes that bump in the pressure that gives you a tailwind further out and keeps all those pebbles out instead of closer in. And so at a certain mass, certain conditions must be met. You have to have a planet that's big enough, but once it's big enough, it's not happening anymore. And so then what happens? The snow line can keep moving inward, the disk can keep cooling off, but there's no more source of water. So the snow line can keep going in as far as it wants, but once there's this guy out here blocking the inward flux of pebbles, water is not going along with the snow line. Right? So then you're like at the base of the mountain the day after a snowstorm, where it's 0 degrees, but there's no snow because it's not snowing anymore. Okay? So that's the idea. And in the solar system, Morby alluded to this as well, there's some meteoritic constraints on when Jupiter formed and may have actually done this, blocked pebbles in this way. And so we're looking at here, it's kind of a rough formation timescale, or a rough timescale on the y-axis. And these different rectangles are basically different classes of meteorites. So the red ones, the basically carbonaceous and non-carbonaceous chondrites, are two isotopically different types of meteorites. And so we think they came from different reservoirs, but they existed at more or less the same time. And so how can that be? We think these guys, especially later on, they were formed at the same time. They're about pebble-sized, but they're not all mixed up. So how can that be? Well, one explanation is that Jupiter's core was already there, keeping things separate. So that kind of fits in the story. All right, mechanism number 2 is a wide feeding zone. All right, you must all know who this is. Cookie Monster. Cookie Monster. All right, so wide feeding zone, what's that all about? So here, cartoon again, because I like using cartoons. So here's a protoplanetary disk with a chemical gradient. All right. Now, imagine you form planets, a planet from just a very narrow feeding zone, right? The feeding zone being where all the components of the planet came from. If you form a planet with a narrow feeding zone, it might look like that. You form a planet with a wide feeding zone, it would look like that. All right, now if this purple stuff has some water in it, this guy would have some water in it, and this one would. So the size of a planet's feeding zone affects its composition. So here's a similar movie that usually I show earlier in talks, but this is kind of what's often called the classical model. It's the model that George Wetherill came up with. And what we're looking at here is kind of the late stage formation of terrestrial planets, in a very simple idea, without any migration, without having a narrow annulus of stuff, just to kind of illustrate what can happen. And here the colors correspond to water contents again. So everything closer in than 2 AU is dry. There's a little bit of water out to 2.5 AU, and past 2.5 AU there's 5% water. Okay. And Jupiter is already formed, and we're going to watch terrestrial planets, bash into each other and grow. So there's kind of a wave of growth that sweeps out from self-gravity going outward that way, and there's a wave going inward from excitation from Jupiter. And this guy here is going to turn out to be a pretty good Earth analog. But you can see it's still red. That means it's still dry. And you can see its color change. So there you go. So its color changed. What does that mean? It got bashed in, something that started off further out that had some water, bashed into it. So that's basically its feeding zone widening in real time as it happens. Well, not real time. It's like millions of years. But you get the idea. Okay? So the color of these things, at the end of the simulation, we have a decent Venus and Earth analogs, and they have a lot more water than was present in the inner 2 AU of the disk because their feeding zones were wide. Here's what their feeding zones look like in that simulation. The color here corresponds to the feeding zone of a given planet. So this inner planet got its material from there. The middle one got its material from that dark blue curve, and the outer one from the red curve. And so you can see all the water came from past 2.5 AU. They all have a tail going out past there. So that's where the water's from in this model. Okay? Of course, as Morby talked about, this model has a key Achilles heel in the fact that it screws up Mars terribly. So this model probably doesn't work. But the concept of getting water from a broad feeding zone still makes sense. All right, the third one I'm going to talk about is external pollution. So what am I talking about here? The idea here is that maybe a planet can form in the habitable zone, mostly from stuff that's nearby, but get this kind of rain of material coming from elsewhere, that provides the water. And so one way to do that is a mechanism that Morby also mentioned this morning, is the idea I'll just kind of summarize really simply. Imagine these are a bunch of planetesimals orbiting the sun. Here's Jupiter's core. Jupiter grows, and it destabilizes the orbits of nearby things and kicks them around. And some of them can go deliver water. And so here's an animation of that process. Here's Jupiter's core, Saturn's core, and the color of objects here are just tags to where they start off. Okay, so everything in the asteroid belt's red, and then green out here, and so on. And so you can see, after 100,000 years, we're going to grow the core of Jupiter, and you'll see it affects things. It kicks things up and all over the place. And gas drag can kind of make them rain down. So a lot of them end up in the asteroid belt. Then Saturn grows later, and it kicks things toward Jupiter and kicks them up. And some of them end up in the asteroid belt. Some of them get kicked past the asteroid belt. And so in this kind of plot, these guys look a lot like C-type asteroids. And these guys up here basically have such stretched out orbits that they cross the orbits of the growing terrestrial planets and can deliver water. All right, and exactly what the ratio between those needs to be matched to reproduce the solar system. But the principle of it, the mechanism itself, makes a lot of sense. Exactly how much it contributed to water on Earth is a debate. Okay? And of course, there's the grand tack model. Here we're showing snapshots in time of Jupiter migrating inward. Saturn catches up, and then they go out. And as they go outward, they go through all these blue things, which represent water-rich planetesimals, some of which are kicked all the way into the growing terrestrial planets. And it looks kind of like this. Here's another movie similar to one that Morby showed, where after Jupiter's migrated in and out, there's this kind of rain of water-rich material that's crossing the orbits of the terrestrial planets. And in time, there we go, things bash into each other, and the little blip in the middle of each of these planets represents, shows that it's gotten some stuff that had water. Oh, there's birds. There really are birds in this park. That's good. All right, so the last mechanism I'll talk about is migration, like bird migration. We should watch a bird movie. All right, so migration, you've already seen this picture. The idea here is very simple. Why would migration affect water content? Well, you can imagine in some cases a planet that ends up in the habitable zone might have started out way out there and migrated inward. In that case, oops, I went too fast. In that case, basically the final location of the planet would be really disconnected from its feeding zone. And so you could end up with something super water rich in a place that started off with no water. Here's an illustration of the approximate migration timescale as a function of the mass of an object. You know, this is for a certain disk model. But anyhow, the point is the terrestrial planets formed from, as we heard, Mars mass things. Those are about a 0.1 Earth mass objects. The migration timescales for those bodies are really long. They're longer than the lifetime of the disk. What does that mean? It means that migration of those bodies didn't play a role in forming the terrestrial planets or delivering water to Earth. Although they could matter in some other cases. So what are the possible sources of Earth's water? The pebble snow thing doesn't work great because there are basically just too many dry meteorites, in particular exterior to Earth's orbit. A wide feeding zone works great. It just screws up Mars so badly that it's not a good option for the solar system. The external pollution works great, so that's why it has a full beer glass. And whether it's just a consequence of Jupiter and Saturn growing or the Grand Tack, you know, that's up for debate, and there's lots of issues going in there. But in any case, those models seem to work pretty well for now. And the inward migration idea is a nice idea, and it's got to matter in some cases, but probably not for the solar system. Now, let's extrapolate this, at least in a very simple way, to exoplanets. So I already showed you this plot of the very rough demographics, one simple way to slice up exoplanets as we know them. So which water delivery mechanisms might matter in different parts of this plot? Well, here, I guess I put them all at once. All right, so for solar system like, external pollution seems to work pretty well. Maybe wide feeding zones can matter. For cases with giant planets on very eccentric orbits or that migrated, external pollution definitely matters. Maybe wide feeding zones, but planet-planet scattering might also destroy your terrestrial planets anyway, in which case you don't care too much. For super-Earths, migration might play a big role. And then the starting location from where the planets migrate definitely matters. Things like the pebble snow mechanism probably matter, and wide feeding zones probably matter also. And as a very final thing, there's some kind of simple arguments you can make in terms of how this would depend on the type of star. So as a function of the mass of a star, you know, the sun being here, this shows the position of the snow line, or basically the orbital distance of different things. So the habitable zone is shown in blue, and the position of the snow line for certain assumptions, right, basically at certain times, is shown in red. Okay? And so what's interesting here is that the snow line is farther away from the habitable zone for low mass stars. All right? The distance here is, you know, it's not a linear thing. Basically, it doesn't matter how far it is linearly. What matters is really logarithmically how far it is. So this really is a bigger distance to traverse than this. And so, you know, how much does this matter? Does this affect what we're talking about or not? And there's a bunch of factors to take into account. So I'm going to tell you a bit about the factors without giving you a final answer because no one really knows the final answer. So some of the factors that matter are that, you know, like I said, for higher mass stars, the snow line is closer to the habitable zone. But for low mass stars, the disk actually lasts a bit longer, so maybe you have longer to do this. For higher mass stars, there's higher mass disks, which can play into, you know, which can play in different ways. For low mass stars, they have more super-Earths, which may have migrated. For high mass stars, there's more gas giants, which might do the external pollution thing. So all these arrows are really just here to kind of show you that there's a lot of factors at play. And so if you want to ask the question, are planets around low mass stars more or less likely to have water on them? The answer is, well, I don't know, you know, there's a million things to think about. And so you have to ask the question very precisely and really have a handle on all these effects. So that was the end of the fifth thing I was going to talk about. So I think I should stop there because it's 5 o'clock. So I'm stopping.